Very good morning all of you for this course river engineering, and we are going to talk very interesting topic river stabilizations, looking these river erosion problems in Ganges, Brahmaputras and alluvial rivers. The bank erosions is a major problem in our country, and looking that I will talk today how we can stabilize the river bank. That is the very interesting topic which is a part of my research study. I will show some of the research study along with these lectures, but let us try to understand it. What is the contributions of US Army Corps of Engineers in the last 50 years in their experience on river stabilizations. That what today I will discuss it, and I will try to make it to as much as possible to understand the mechanics behind them. Also there is a design guidelines which is a partly is a embedded from the field experience. There are the design guidelines are there. So, I will talk about basic physics and basic river mechanics, as well as I will talk about the design guidelines for river bank protections. That is what my objective today. And if you look at this way, and mostly we are following this book, the river mechanics P.J. Julian books, which is very concise book on the river stabilization chapters, and not only that other books are there just for the more reference for this. Look at the next part, just if I give a introduction, see that how the platform of the river varies it. It is quite confusing, right? You nowadays it is quite easy to map the platform variability of a river with different time span, because you have we can get the satellite imageries which is almost free of cost. So, if you look at the satellite imagery analysis of the Kameng river, one of the tributary of Brahmaputra rivers, and if you look at that how this bank lines migrations are happening it. This is the right bank, this is the left bank, and you can see this 88 and 2002 how the bank line migrations are happening it, how the bank erosion process are happening it, which is quite significant order as compared to the world level also. And why it is happening it, that if you look at the bank materials, erodal bank materials, okay, look at this, the height of the river bank, which could be a range of more than 6 meter, more than 6 meters. This is the height of bank. So, we can see it that, and some river protections like a geobank, we have been doing it to protect the river banks. So, we have a lot of experience in the last 1 or 2 decades how to protect the river banks of Brahmaputra rivers, Ganges and other alluvial rivers. So, we try to have a understand it how we have to design the river bank protections work as technical as possible. That is the idea today. We will have a more discussions, and if you look at the next slides, it is showing about in different year from 88 to 2016 is almost 18 years, how this river width is varies with reach numbers along the length, how it is varies it, you can see it. So, each year there is a variabilities in terms of width of the river, the width from the left bank to right banks. If you look at that, width is considerable. In some of the locations as high as it goes about 4 kilometers. That is quite interesting if you look at it, and some of the cases it goes as lesser than 500 meters, 500 meters, and this is what 4 kilometers. Just try to understand it, how river has so dynamicisms in terms of manifestations in terms of platform variability, and if you look at, if I look at the left bank and the right bank, you can see the figures. It is quite interesting, shows the erosions and the depositions. The positive part is erosions, the negative part is depositions. If you look at the trend what is happening it, there are the trend like this and there is a trend like this. Two processes are happening it, and that is what is reflecting on this. Whereas if you look at the right bank, most of the time this process goes like this. Why does it happen this? How can you protect the rivers bank? It's a quite challenging task to protect the river bank when you have a looking the satellite imagery, just do the satellite data imagery analysis, you can see that how the erosions depositions patterns are changing it, how this with a temporal domain, how the erosions depositions are changing it, and it is quite interesting for us. Can we protect the river banks for this type of so dynamic river bank erosion process are happening? It is a really a big technical challenge, but let have our knowledge can help us to make it appropriate river bank. If you talk about bank erosions process, how it happens it. If you look at any of the during the monsoon periods or the flood periods, the bank erosions losing the land mass is a quite evitable, like a river like Brahmaputra, river like alluvial rivers. These are quite every year we heard about that. But if you look at this bank erosion process, which is a part of Brahmaputra rivers, okay, if you can see this height of this, if you just compare with this height of the main, okay, which will be about 6 feet, and you can understand it, this may be more than 18 feet, okay, more than 18 feet. This height of the bank, river bank is collapsing it. You can see the collapsing the river, you can see look these figures, it tells many story to us, how bank erosion process happens it. Just look it. So, it will be more than 18 feet, okay, and that is what is undercutting of the rivers are happening it, and this mass cantilever failures, crackings, even the trees are falling down it, and if you look at these habitats. These are quite, these are similar figures, photographs you can see in many part of Brahmaputra basins and the Barak basins having the so high erosion rates happens it during the flood periods or the receding of the flood periods. Let us understand the process. What is the process happen? See, if you look at that, when you talk about a straight channels, okay, simplified as a rectangular channels, and if H is a depth of the flow, we know it, the average bed stress what is again working is omega r s or omega h s. S stands for here, we can consider is a bed slope. So, the mostly the H varies it, the shear stress is increases. So, that is what is a proportionality. Okay. So, we can say it, the shear stress acting on the bed is a proportional to the flow depth. Higher the flow depth, more the shear stress acting on the bed or average shear stress. But if you look at, try to look at how the shear stress distributions happens it, you can get it the shear stress distribution something like this, similar to this. That is what is the shear stress distribution. So, there are the shear stress acting because of the flow, because of the turbulence behaviors. We know it, what will be the average applied forces per unit area, that is what the shear stress acting it, which is having proportional to the flow depth. As the higher return period about the flood comes it, there is a more likely to have a more shear stress, there is more applied force per unit area acting on this. That what will try to erode the bed material and as well as bank material. That is very basic things. Okay. So, very basic things concept if you try to understand it, as you will have a higher depth of the flow, higher the applied shear stress acting on river bed and the river bank, then it is going to erode the bed materials and also the bank materials. That is what is happens it. But if you look at that, one is the process is that how the bed shear stress and the bank shear stress acting on a straight rivers. But many of the times you know it, the river meanders it. That means river have the curvatures. That's what it. So, you have the river curvatures, as you know it, there will be the secondary current generations will happen it, and because of that you can see that upper streamlines will act like this, whereas the bottom streamlines will act like this. This is the upper streamlines and the bottom streamlines. So, that the process is happening it. This is the upper or streamline, this is bed, river bed streamline. See, try to understand it. That is what it happens, the secondary current formations. How does it affect to in terms of erosions? The outer banks is more vulnerable because of this process what it happens it, the secondary current. That is what you can look it from these figures. What it happens it, if you look at the outer streamlines, pre-surface streamlines and bed streamlines. So, one is attacking this outer bank, another is lowers the streamlines which are bringing the bed materials to the from inner bank to the from outer bank to the inner bank. Just try to understand it, how it happens it. So, if you look at these pre-streamlines are behaving like this, and you have the bed line streamline is working like this. Because of that, there will be outer bank erosions and the inner bank depositions process. That is what you can see in terms of the process what it happens it, and the depositions here and erosions here. So, you will have a outer bank, and this is a line which is called the thallic lines. This is a line we call the thallic line, how these depositions patterns are happening it, and how these thallic line shiftings are happening it because of this process. So, river banks are accelerated the bank erosions at the outer bank, also it facilitates to have a deposition in an inner bank. That is the reasons the point bar formations happens at the inner bank. So, the secondary current, strength of the secondary current, the geometry of river band in terms of radius of curvature, in terms of the flow depth, in terms of the width, those are critical points for us to know it, what is the strength of secondary current, and because of that what is the patterns or the flow strength in terms of flow streamlines at the surface at the river bed level, and how the erosions deposition process happens. So, in case of river band, it matters for us to know it what is the strength of secondary current and what is the geometry of this river band in terms of radius of curvatures, in terms of width of the flow, in terms of the depth of the flow. That is the matters of us, because that is what initiates the bank erosion process. And erosions and depositions, both the processes are initiated because of this secondary current, besides this applied shear stress acting on this bed. No doubt, let me go for the next level, how the bank erosion process happens. It is not the same things happens everywhere. Like some of the case you consider this non-cohesive bed, means there is not significant the cohesive strength on the bank materials. That means, as close to a sand materials there is no cohesive strength. In that case, if you have an angle of repose and because of higher the stress, there will be two coating will be there, two toe coating will be there. So, the toe part will be caught it, and this will be as a slice, it will slide down it, because as soon as the angle is more than the angle of the repose, then of the bank materials, that is the sliding will happen it for non-cohesive banks. But please remember it, in generally the river bank is not a non-cohesive nature, it is a combinations of the both, that is the stratified bank. or you have the cohesive bank, means you have a silt and the clay compositions along with the sand. Okay. That is most of the times we see the rivers which will have a non-cohesive natures, where you will have a silt, clay and some part of sand mixings. That is what whenever you go to the river bank you can see like that. So, if you look at that, what it actually happens here? When you have a low flow, if you look at these figures, if you have a low flow like this, as it goes to the high flow, your groundwater tables will increase it. The water will be go from the river to the bank. Water will be shifted into the river bank. But what it actually happens is, when the flood recedes, when it goes back from high flow to the low flow, this saturated mass, additional mass strength comes here, okay, as compared to the low flow earlier. So, this is a saturated mass, the soil mass. Because of that, it makes failure cycles and it has a rotational failures like a landslide problems. Okay. So, you try to now understand it, bank and fail like a landslide problems, and that what is during the receding phase of the floods, not the rising phase of the flood, because when the flow depth is decreases, in that period this process happens, the saturated mass give a additional weight to this block, and we have the, as we know it for in landslide failure mechanisms, exactly same things happens, the less stables and the rotational failures happens. You can do a geotechnical analysis to know it with how, what type of geotechnical failure cycles, failure surface and all the things you can understand it. But some of the cases like alluvial rivers, as we studied more detail for the Brahmaputra rivers, we will have a stratified layers. That means what we have? You will have a compositions of a clay, sand like this. So, you will have a some permeable maybe sand filled with the clay layers, then clay layers, and then will be sand and clay layer. These are general depositions of the alluvial rivers. It can have a stratifications of the sand and the clay layers. If you have that case, that is what is in generally in alluvial rivers in our country, we see this type of bank stratifications. There will be bank stratifications will be there. Where do it happen? It when the river flood comes, it or the monsoonal flow increases, the water shifts into inside these permeable layers. Water shifts into this permeable layer. As it shifts into the permeable layers, as it recedes, the water also comes back it. Because of that, you will have the top surface cracking, and you will have the cantilever type of failure mechanisms will happen it, and you will have a mass wastings like this. So, try to understand it. There are three the bank characteristics how it controls the bank erosion process, like non-cohesive banks, which generally does not happen it except some cases where the undercuttings will happen it, and the non-cohesive material like a sand, there will have a failures surface, the slicing failures will happen it. If you have a cohesive banks, you will have the rotational cycle failures, slip failures. That is what it happens in the, as you do a embankment design and all, you look at that, the same concept what we have to look at how the failure mechanism happens it, but we have to consider how the flow depth variations are there from low flow to high flow to the low flow. Similar way, if you look at the stratified bank, which is more common in alluvial rivers like Ganga and Brahmaputra, and that is what it happens it, how the block failures are happens it. These are the process understanding, we need to know it. Cantilever failures with a tension cross, you will have a rotational fluid with a pressure and tension cross, you will have a shielding failure. That is what the basic failure mechanisms happens it, and we should try to understand the failure mechanisms, go to the field, observe the bank erosion process, and try to understand what type of mechanisms are happening at the field. That is more important before stabilizing the rivers bank. That means you are strengthening the river bank, okay, by revetment or any process, or you are modifying the hydrodynamic characteristic near the bank. These are two processes what you try to do it, but before implementing any river bank protection work, we should visit the field, try to understand what type of bank erosion process are happening it, which is more important before designing any river protection work. Now, if you look at the basically you can understand it, what are the forces is acting it, it's very simple things. It's a flow parameters in terms of discharge magnitudes, durations, the velocity, apply shear stress magnitudes, and also orientation. Similar way, we need to know it what type of bank materials are there are gradations, there are cohesions, and biological factor like vegetations, and artificials like urbanization, drainage, floodplain farmings, development, water level fluctuations for the hydropower projects. All we should try to understand it and try to incorporate it. Why the bank erosion process is accelerating? What is the reasons behind that? That's the needed to understand all these active forces, passive forces, biological factors, and man-made or artificial induced activities like the water level fluctuations due to hydropower generations, floodplain farming also it happens it. Even if commercial navigations also play the roles for bank erosion process, that all we try to understand it. Now, if you look at what are the factors affecting the stream bank failure, as I discussed on the river bank processes, is that significantly we should understand the floods, okay. How significantly changing the channel geometry. We should understand the sediment transport capacity during the high flood events. That's the period we will have the bank erosion rate will be much more higher rate. Okay. So, that is the reasons we should try to understand the flood characteristics which affect the channel geometry, also make a edge higher order of sediment transport capacity. Then we should try to understand these landslide cases, that small landslide type of failure mechanisms happens it on the river bank because of fluctuations of groundwater tables, the slope variations that may be the causes because of earthquakes also can play the major role to triggers the landslides process at the river bank. You can also understand the presence of water in the bank. That is what is outflow of water from the river to bank, stabilization of the river, inflow of water from bank to the river, that is what is destabilization of the bank. Just try to understand it as I explained earlier. And if you have a stratified bank, there will be a piping process which you will have a remove the particles, okay, or delodging and transporting the fine particles from the permeable lens. That is what it happens, the piping process. Then you will have a mass wastings, that means there will be a block of the banks sliding, sloping into the rivers. That is what it happens is, and you also look at that additional structure, the saturation process, infiltrations, all you try to understand it, to know it, how the bank erosion process are accelerated or decelerated because of flood, landslide process, presence of water in the river, presence of water in river bank, piping, mass wasting, that the process and how we have intervene all these things we should understand it. Now, if you look at what very basic engineering things we can do it, okay. The basically concept is saying that you change the slope, okay. So, make it the bed slope, the reduce the slope. Okay. So, that is what is called slope reductions benching process. Okay. It is a very simple things. Like for example, you can have the soil is removed from the slope, flatten the slope angles. Basically, you try to make a slope reduction method. The bank slope you want to reduce it. So, what you do it? You just cut these materials and fill it here. Okay. This is earlier bank. After cutting, you reduce the slope. This bank material you cut it and dumped it here, and you put the stone riprap or the Gaussian matrix on this. So, that is what the cut. It is a very simple things. So, same way you can reduce the slope of the bank, flattening of the slope, use of fill materials. We are filling these materials. After that, top of that, we have a stone riprap, or you have a cut and fill. So, you can understand from before and afters, there will be partly cut, partly fill up, then you will have a stone ripraps or the Gaussian matrix or any riprap concept. We will see that nowadays geotextile riprap also we are doing for the smaller rivers. So, basically to reduce the slope of the river bank, which will be stable slope, or you can have a benching process. If you have a river is very wide or the depth of the flow is much larger, you cannot do it cut and fill or the fill, you can have a benching. So, that will be the bench will be there, the cut and fill will be there before and afters. After that, the final shape of the rivers will come like this. This is the before, and you are making this after concept like this. See, if you look at that, then you also have a stone riprap. It is a very basic things we can do slope reductions of the river bank using cut, fill, cut and fill or the benching process. You can visit any of the river bank, you can see where river training are there. The most oftenly they use this slope reductions methods, which are very simple things to do it. Now, when you will do it, as you know, these groundwater fluctuations play the major roles for the two failures or the rotational failures. How we have to reduce the fluctuations of the groundwater tables? That the what we do it, you provide subsurface drainage, control the groundwater within a slope. That is what we try to do it. How do you to do it? If you look this figure, you can understand it. Is horizontal drain. So, we can have a drain, we will have a horizontal drains, and we have a pervious materials, the permeable materials, or maybe the sand and all, and you can have a pipe arrangement, and you will have a impervious plug here. So, that way water will sift through these ones, and that what will reduce the fluctuations of the groundwater tables. So, this is the subsurface drainage systems with a horizontal drains. Okay. So, it needs to do it, otherwise the groundwater fluctuations will be there. Or you can have a drain well. So, we can have a drain well. So, you can have a this, and you can see before groundwater table like this, because of this drain well, the groundwater tables decreases like this. Nowadays, it can be done it many numerical softwares are there. You can see that how much of effectiveness of the subsurface drainage, that is what we can do it, but theoretically you can know it, it will happen like this. So, we can have a drain pipe, we can have a well to collect all these materials, and that what will be water to put it, and you will have a stone riprap or the Gaussian matrix. Same way you can have a trench, okay. You can have a trench, and you can see this groundwater tables earlier, and because of the trench the groundwater tables like this. So, it has a lot of change, and basic your idea to protect it too with a riprap, and also reduce the rotational failures, control the groundwater table fluctuations, or in the river bank. To do that, we should provide the subsurface drainage along with river bank protections. Along with river bank protections with having a horizontal drain, vertical drains or drain trench. All the combinations we can look at which is a suitable for appropriate river locations and what is the groundwater fluctuations are happening it, and we can geotechnically and hydraulically we should design it, how the groundwater fluctuations will be there, how we can have a two protections. That is what we can do it. Now, if you look at that, when you talk about the river bank protections, if you look at this is a simple textile based river mattress, okay, textile mattress, okay, they are just this is a small river, they can put a textiles jute type of materials and can have a just protect over the bank with the filters and all. So, there is not a single solutions for a same type of river protection for all the rivers. That is the reasons we should look at what are the advantage and disadvantage, because it should be flexible, construction should be simple, special equipment are not necessary and durable and recoverable. It is basically any civil engineering concept we look at that we should have a locally available materials and constructions should be simple, it's not be so expensive, because we do in a very remote state non-accessible point where the river bank erosions are happening it. So, that is the basic idea, should look at how the river bank protections we can do it. That is the point we should try to understand it, because the cost of river bank protections per kilometer is close to the cost of national highway construction per kilometers. So, please try to understand it. The cost of protections of the river banks is much expensive of constructing a highways, national highway per kilometers. They are more or less same, or many of the cases is much higher order of that. So, when we are trying to protect the river bank, we should try to optimize everything in terms of material, in terms of construction cost, in terms of this. Otherwise, cost of a river bank protections per kilometer is close to the cost of the national highway constructions per kilometer. That is the point I want to highlight to you, that we should not take so lightly just dump the stones, okay, on the river bank, and you feel that river will be protected by just dumping the stones. That is not the because US Army crop of engineers, they have done a very significant studies and remarkable success stories in rivers in the USA as particular to the Mississippi rivers. So, we should take the knowledge from them. It is not that we are just to dumping the stones on the river bank to protect the bank. That is not be the idea should to be a river engineers, because it is a very expensive work, because cost of the river protections per kilometer is as close as to the cost of the highway constructions, national highway construction per kilometers. That is the reasons we should take the knowledge what we have from US Army crop of engineers, and because that successful stories and the local knowledge, both we should inbuild it to make it a successful story for river bank protections or river stabilizations. So, if you look at that, there are points for the rock riprap joints. We all talk about protect the rock riprap, or you put the stone gabions, you put the any geotextile mattress. We should know it that what type of stone ripraps are coming it. It all depends upon velocity, side slope, density of the rock, angle of repose. Riprap blanket thickness, you can know it, you can have the you can have the thickness, the providing this thickness, those the things you can consider it as a Gaussian matrix. Filters should be provided between the bank and blanket to allow the seepage to prevent the erosion of bank soil through the blankets. Okay. This revetment can have a considered as a blankets with a Gaussian matrix and all. In that case, we should provide the filters between the bank and blanket to allow the seepage go through that. So, it can reduce the seepage forces. Okay. Blanket must be tied into the bank as it is in upstreams and downstream ends. I will show the photographs in the end of these presentations. So, if you look at this, what is actually happens is that how to design the rock stone riprap. As I said it, please do not put it the stone just on the river bank and it will have a without any engineering knowledge, stone dumping on the river bank does not suffer stabilize the rivers or protect the river bank, because we have to understand the physics behind that. That is what we should look at the shear stress methods. We should look at the shear stress methods. Again, I am to sketch it. If you have a river, you have a flow depth. If you are not considering this any bend of the river, there will be shear stress distributions along this, and this shear stress is a proportional to flow depth. Okay. So, we need to compute it. If I am putting the river bank materials, a stone riprap, I have to do particle stability analysis for this stone, whether these stones are stable with respect to the flow, shear stress acting on these, turbulent structures acting on these, whether these particles stability or the stone stability we should look at. That is what is there. The riprap stability depends upon the direction, magnitude of the flow velocity, side slope angle, the properties of the rock, all the properties depends upon that. That is what is the shear stress methods gives us. And if you have a Manders, if you know it, there will be deflection angles which is a function of 11 h by r. H is the flow depth, r is a radius of curvatures for a natural Manders. You can additionally consider, because of meandering, what are the stability of this stone stability, which earlier we defined as a particle stability. We should try to look at as a stone we have when you are dumping over these rivers during the stream flood situation, whether these stones are stable at that positions. So, we should do stone stability analysis as close as the particle stability analysis what we discussed earlier. So, if you look at that, you can have a certain assumptions. Okay. The specific gravity of the stone 2.65, and you can show it downstream bed slope is negligible, absence of the secondary flow. Now, if you look at the design of shear stress methods, as I said it, you can consider is a particle stability analysis, as you are dumping the stones as equivalent to bed material particle stability or bank material particle stability. We can analyze it and find out the relationship between size of the bed particles or the bank particles in terms of a functions of theta y applied shear stress. As discussed earlier, you will have a silt shear stress, that is what the critical value of the silt shear stress. You have specific weight of the rock, water respectively, and you have a angle of repose and side slope angles. These are functions already we derive in particle stability analysis. The same concept we can use it to compute what will be the dm size for that. That is what
coming to a functions with a applied shear stress versus a functions of
theta 1 is a side slope angles and the phi is the angle of repose, and you also have critical value for shear stress for the shield numbers. That is what you already we discussed earlier. Now, if you look at with a very simple problems that determine the rock riprap size required for stabilizing the banks of a straight river, given the river width is W is 370 meters, the flow depth is 6 meters, channel slope is 50 centimeter per kilometer, bank angle is 30 degree, density G is 2.65, angle repose is 40 degree. So, simple cases. You just use this, compute the applied shear stress which is a functions of flow depth and the slope is given. So, we can find out the shear stress what is acting is close to the 30 pascals. Okay. And you can also compute it basically that component, and finally, you can compute it, you can assume the critical shear stress value which already earlier discussed that we can consider critical shear stress is 0.047, and for that respectively you can substitute this value, then you can compute it. It is necessary to have a 3 inch, it is very smaller, okay, close to 2.2 inch depth of river bank protections what you need it, okay. And that is what is a simple calculations we can do in Microsoft Excel or anything. You can try to understand it how, what is the thickness of the bank materials stone riprap size is necessary. Knowing this flow characteristics, bank slopes, rock characteristics in terms of density, the critical shear stress, we can make it get it the value of what will be the thickness for stone riprap. Now, if you look at there is another methods which called the velocity methods, which depends upon if I know the velocity of the flow, we can know it, or if you design, you consider design flow velocity, then you can find out what could be the size of the dm of a stone riprap size. See, if you look at the concept is come it same way that if you consider a D50 value, okay, so this having a D50, 50% finer particle size distributions, if I know it diameter of that, and if I consider, if you look at that, the velocity against the stone at the top of this, okay, if I, what should be the top of the velocity Vs, okay, on the top, that what can be written as a functions of shear stress, shear velocity, we can write it. This is our empirically conducting a series of experiment. It found that the for a stone riprap, the velocity at the top of the stones is a simple functions of shear velocity. Okay. Since it is a shear velocity functions, we know the relationship within the shear velocity and ds with the tan phi. We know it earlier in terms of critical shear stress numbers. So, we just substitute that, then you can find out what will be velocity at the top of the top of the stone riprap in terms of functions of 2 g minus 1 ds and tan phi. Just substituting these values, we can understand it. Now, we cannot compute is the Vs value, because we can know average velocity for a, or we can design velocity maybe 3 meter per second, or maybe 5 meter per second, maybe 2 meter per second or 10 meter per. So, we can have a design velocity, but we cannot have the exact value of the velocity at the top of the stone. But again there is a empirical relation, the logarithmic
relationship with flow velocity with respect to the velocity at the top of the stones and relative submergence h by ds, okay, hf ds values. So, that the empirical relation. So, we can again substituting these two relationship, empirical relationship, the finally we can get it the Vc, the critical velocity or design velocity, what we consider it is a function of Kc. Kc is a with a function of h by dx, which is the relative submergence h by ds, you can understand it, and angle of repose, that is what, and you have a the ds value. So, that means if you look at this graphic, is a design chart is provided by US crop of armies, US Army crop of engineers. So, if you look at that, very interesting design chart has been provided. In this axis the diameters, equivalent spherical stone diameters, this is the stone weight, okay, because you know the specific gravity, you can find the stone weights. This side you have the velocity, and there is a curve of Vc equal to this ones. There is a regions of stable and the unstables, and these are this curve for different slope, okay. 3:1, 2:1, we have a different slope, okay. This is called design charts. You do not have to remember these equations, you just to have a design chart. That means, if I consider my flow is 3 meter per seconds and I am designing for this case slope, we can find out what will be the equivalent spherical diameters. Just opposite of that, what will be the stone weight, that is what also I can find out. So, same way I should consider in stable regions, not the unstable regions. So, we can consider this is a 4 meter per second is the velocity, the slope is 2.1, for that what will be this case. So, we can always look at what will be the stable dimensions of the stone riprap from this design charts. These the design charts are made by extensive experiments as well as empirical relationship and the field experience. They create a, they have prepared a design chart which we can use it just to know the design velocity, know the slope what we have to maintain it, for that what could be the appropriate the representative size D50 size of stone riprap. That is the design chart, and that what we can use it to design the riprap part. If you look at that more detailed things, that you need to have a gradations, because a single side uniform stone will not get it from the natural cases. You will have always a gradations of the stones what you will get it, and most of the times in the river when you have the scouring process, the turbulence process are there, stone the because of well graded river bed materials, and we can take advantage of armoring the layers. The smaller and bigger size they can prepare a armoring plate, okay. So, that is what advantage we can take it. So, that is the reasons we should have the gradations, we should not have the same size, and we should have a DM, the effective size is a D65, which will be 1.25, because we are so often we use a D50 value, but when you talk about the rock size and well gradations part, if I talk about then we should represent a D65, which is representing that, which also we know it is closer to 1.25 times of D50, and should have a angular stones which is suitable than the rounded stones, and pore gradation of the rock can be used for riprap. Then we should have a proper design of the filters, okay, the filter materials, otherwise bank and bed materials can collapse it. Now, if you look at some of the design guidelines is given by this is particle size distributions of the riprap gradations. You have a D50, ship size, percentage of weight. Okay. So, if you look at that, you need to do a geotechnical investigations to know the stone materials what you have, and the US Army Corps of Engineers, they have given from their field experience all these design guidelines. It is a very interesting thing. These are all their field experiments. They say that there should be a upper D100 should not exceed the 5 times of lower limit of D50. Size that can be obtained economically from the quarries, because the stones with a different size cannot get it. These all are natural sense stones. So, that is the reasons we should have a target to bring the stones from natural quarry which is nearby one, and size that satisfy the layer thickness requirements. Okay. And the lower limit of D100 stones should be less than the 2 times of lower limit of D50, and similarly lower limit of D15 should not be less than 1/16th of upper limit of D100. Bulk volume of the stone lighter than D15 should not be exceeds the volume of the voids in structure without these lighter stones. This look the design guidelines what they have prepared it, looking having a lot of experience in the stability of stone riprap. The US Army Corps of Engineers, they have followed these guidelines. Okay. Just follow the guidelines, because that is what is advantage for the stability of stone riprap. That is what the upper limits, the lower limits, and design guidelines what they have been prepared. So, if you look at that way, also they have a gradations. Riprap thickness should not be less than 30 centimeters. That is what the minimum. That means 12 inch should be. The diameter of upper limit 1.5 times of diameter upper limit of D50, whichever we get us. The riprap is placed under water, the thickness should be increased by 50%, because many of the times to protect the scours, the toe scours, we apply lay this riprap under the waters, the thickness has to be increased by 50%. And it also look at that if there is a floating debris, wave actions. Okay. In that case, you have to have a increase by 6 to 12 inch additional things to be put it, okay, which is 15 to 30 centimeters. So, if you look at that, these are all design guidelines considering that because of debris, because of underwaters, stone ripraps we are doing it, which we can increase by the 50%. So, all you look at, we US Army Corps of Engineers, based on their field experience, they have given these guidelines, which is already has been applied for many of the river in US, and they have been successful in terms of designing this part. So, with this let me I conclude today lectures, and in the next class we will also further will discuss on this more details, how to design the filters and other part. Thank you very much.